Yeah, good evening, everyone. Can somebody please confirm? Like, are you able to hear me? Am I audible? Okay, thank you. Good evening, everyone. Myself Shankar Rao, a PhD scholar in the Department of Electrical Engineering, IIT Hyderabad. So today we will discuss about some of the topics from signals and system. That too, we will discuss about LTI systems. In last class, I think somebody has asked about LTI systems and their properties. Uh, Today we'll discuss briefly about LTI systems and some of the problems based on them. Yeah, we will solve. Fine. Today we'll see about LTI systems. A system is set to be LTI means linear time invariant. It is said to be LTI if it satisfies both linearity and time invariant properties. Time invariant properties. Okay. If it is linear and time invariant, then the system is called LTI system. So now what is linearity? We'll see now. So we will say system, I think you might have studied already this. The system is said to be linear if it follows two properties. One is additivity and homogeneity. Okay, let us say we have some system, and if we are giving some input x of t, the system does some operation on the signal input and we will get output. So the output is nothing but some transformation on the input signal t of x of t. Okay. Now let us say if I am giving x1 of t as input to the signal system, then the output what I get is, let us say, y1 of t. And if I am giving x2 of t as input, output I am getting is yt of t. That means this one is nothing but t of x1 of t and t of x2 of t. Okay. Now, when I am giving both the signal together, x1 and x2 together, if I am giving, let us say the output is some y dash of t, something y dash of t. Now, if this y dash of t, if this is equal to t of x1 of t plus t of x2 of t. That means when I am giving input as combination of x1 and x1 plus x2, then let us say the output is according to this t of x1 of t plus x2 of t, because this as a single signal and we are giving. Now if this is equal to y1 plus y2, if this is equal to t of x1 of t plus t of x2 of t, okay, then the system follows additivity property. Okay, so if I'm giving individually x1, then I'm getting output this one y1. If I'm giving this, then I'm getting output this one. Suppose if I'm giving together x1 plus x2, then this is the output. And if it is equal to y1 plus y2, the individual outputs, the combined output is equal to individual outputs, then we say the system is following additivity property. Okay, and this is called additivity. And the next property is homogeneity. So let us say, so this is our system. If I'm giving x of t as input, let us say I'm getting output y of t. Suppose if I scale the input with some alpha, if I'm giving as input, okay, if I scale the input signal and I'm giving as input, then let us say I'm getting some output. So here what is the output? This output is nothing but x of t, the first case. So t of x of t. In the second case is output is nothing but t of alpha x of t. Now if I scale the input, I'll get some output. If this is equal to scaled version of the previous output, so this one, then that is called homogeneity. The system is following the homogeneity. Hope you understood it. So if I am giving scaled version of input, and if this is equal to alpha times of this one output, this is alpha times of this y, then the system is, we will say the system is following homogeneity. Okay, so this is called, sorry, homogeneity. If the system is following both additivity and the homogeneity, then the system is called linear system. Okay, if the system is following both additivity and homogeneity, then the system we'll call as a linear system. Let me take one example from that we'll try to understand. Let us say we have some system y of t equal to d by dt of x of t, and another thing is this is one system. Now can somebody tell me whether it is linear or not? Can somebody please tell me whether it is linear or not? Yeah, differentiation operation is linear. So how linear means, we'll see here. Suppose I am giving input. So the system, what is the operation of the system? This one. Okay. Suppose I am giving input x1 of t. Okay. Then output is d by dt of x1 of t. Suppose if I am giving another case, I am giving input x2 of t, then output is what? D by d. This is y1 of t output. Let us say this is y2 of t. Now this is d by d2 of x2 of t. Now if I combinedly give the input x1 of t plus x2 of t together, if I am giving, then what is the output? Let us say that output is y tilde of t something. That is what? D by dt of x1 of t plus x2 of t, right? Now this I can write as, since differentiation we can expand like this, d by dt of x2 of t. Okay, now this is nothing but this y1 of t, and this is nothing but y2 of t. So when combined input I am giving, the output is equal to the individual outputs. This is combined output is equal to the individual outputs. So y1 of t is when x1 of t is giving alone, and y2 of t is when x2 of t giving alone. So we can say it is following linearity property. And similarly for, sorry, additivity property. Similarly for homogeneity, let us say if I am giving alpha x of t as input, what is the output? D by dt of alpha x of t. So this I can write like d by dt, alpha into alpha constant I can take common, d by d of x of t. So this is nothing but alpha into y of t. So it is following homogeneity also. So it is, since it is, so it is linear. Okay. Now another example I am giving, y of t is sine of x of t. This is the system, sine of x of t. Can somebody tell me, is it linear or not? Is it linear or not? Y of t is sine x of t. Non-linear, exactly. Now let us say if I am giving x1 of t as input, then what is the output? Sine x1 of t, right? If I am giving x2 of t alone, then it is sine x2 of t. Suppose if I am combinedly be giving x1 of t plus x2 of t, then the output is what? Sine of x1 of t plus x2 of t, right? But I cannot express this, right? So we know sine a plus b is not equal to sine a plus sine b, right? Is not equal to sine a plus sine b, right? So this, that is sine a cos b plus cos a sine b. So this is not equal to this one, right? Sine of x1 of t plus x2 of t is not equal to sine x1 of t plus sine x2 of t. This is not equal to this, right? So it is not following additivity. And also, suppose if I am giving alpha x of t as input, then the output is what? Sine of alpha x of t. Actually, this is not equal to alpha into sine x of t, right? This is not equal to alpha into sine x of t. So this is not following even additivity also. Sorry, homogeneity also. So it is a non-linear system. So hope you understood what is a linear system. If it follows additivity and homogeneity, then a system is called linear system. Now we will see what is a time invariant system. What is time invariant system? Let us say we have one system and input x of t we are giving and output something we are getting y of t. So now let us say I am giving shifted version of input signal. Okay, x of t minus t naught, in shifted version of input signal. If I am giving at that time, let us say I am getting output to some y1 of t. Okay, let us say I'll say when I'm giving shifted version of input signal, then the output I will say y1 of t. Okay, now I am shifting the input, then I'll get some output. Now if this y1 of t is equal to y of t minus t naught, okay, then it is called time invariant system. That means if I am shifting the input signal by an amount of t naught in the time axis, I'm shifting by an amount of t naught, then the output also should shift by the same amount. Then that system is called time invariant system. So to check for any system whether it is time invariant or not, first you find out output due to shifted input. So here y1 of t is what? Output due to shifted input. It is x of t minus t naught. Output due to shifted input is that is y1 of t. Let us say. And directly shifting the output. So y of t is actual output rate when you are giving x of t as input. Now you directly shift the output. Shift the output. So that is y of t minus t naught. If these two are equal, then it is called time invariant system. Otherwise, we will say it is a time variant system. Okay. So time invariant system means if you shift an input signal, let us say I have the input signal something like this. I don't know exactly, something like this. So some 1, 2, 3. Now for this maybe I have some output like this, maybe some 5 to 9. Now if I shift the input signal by some amount, let us say I shift the input signal by 2 seconds, then it will go from 3 to 5. Then output also should shift by the same amount. The output should be same, but it should be shifted by 2 seconds. Okay. The input, whatever time shift we are doing for the input, that same is reflected in the output, then it is called time invariant system. Okay. So let me take one example of a time invariant system. Let us say y of t equal to x of 5t. Now, can somebody tell me, is it a time variant system or time invariant system? Let us say some 5 into x of 5t. Somebody tell me, is it a time invariant system or time variant system?
Sir, is it time variant system, sir?
Okay. Wait. Time variant system. Since time scaling is there, here actually time scaling is there, so it's a time variant system. Okay. X of t cos 2 pi fct. Okay. You tell me whether it is linear or time invariant. Is it linear or not?
Non-linear because of cos.
Actually, linearity or non-linearity we need to define with respect to input, not with respect to any other function. It's a linear one. Yes. Suppose if I'm giving x1 of t as input, then output is, let us say y1 of t, x1 of t cos 2 pi fct. And similarly, if I'm giving x2 of t, then y2 of t is x2 of t cos 2 pi fct. Now if I'm giving both together, then it is what, x1 of t plus x2 of t into cos 2 pi fct. Right? Now can I expand this like this? So x1 of t into cos 2 pi fct plus x2 of t into cos 2 pi fct. So this is nothing but y1 plus this is nothing but y2. This is a linear system. Is it okay? So cost is a separate signal. We need to consider with respect to input. Okay, suppose if the signal is something like this, suppose the system is given as y of t is cos of some x of t, then it is nonlinear. Cos of x of t, then it is nonlinear. So this is linear. What about time invariance? Is it time invariant or time variant? Time variant, yes. First, we will consider
Sir, should I check for homogeneity property also or only?
it will satisfy homogeneity anyway. It will satisfy. We can check. It will satisfy.
Okay.
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 Now regarding time, whether it is time variant or time invariant. Now first, we will find out the output due to shifted input. That means if I shift the input, okay, if I shift the input, what is the output? X of t minus t naught. Only we are shifting the input, 2 pi fct. Okay. Suppose if I directly shift the output, that is y of t minus t naught. If directly shift the output, then what we get? X of t minus t1 t naught into cos 2 pi fc t minus t naught. This is output due to shifted input. This is shifting the output by t minus t naught. These two are not equal, right? These two are not equal. So it is time variant system. Is that okay? See, first output due to shifted input x of t minus t naught, only input only shifting, this one, into cos 2 pi fct. Okay, and directly shifting the output. That means output we know y of t. In y of t, at instead of t you replace t minus t naught. At every t you replace t minus t naught. So these two are not equal. So extra in cos, if we expand extra terms, we'll get, right. So this is a time variant system. Now while coming to the previous example, something we have is y of t is 5 some, what is that, 5x of 5t, x of 5t. Now if I shift the input, the output is 5 into x 5t minus t naught. Output due to shifted input. So x of 5t minus t naught. Now if I directly shift the output, so here wherever there is t, instead of t you replace t minus t naught, directly shifting the output. So that will become 5x of 5t minus t naught. So this is 5 into x of 5t minus 5t naught. Here 5t minus t naught, here 5t minus 5t naught. So both are not equal. It is time variant. The earlier question. Is that okay?
Yes, sir.
So when we are shifting here in x, so here you'll get 5t minus t naught. Directly shifting the output, in the output wherever there is t, we not to replace t naught. Okay. So if the system is linear plus time invariant, then that system is called an LTI system. Okay, the system is linear plus time invariant, then it is called LTI system. Now next we'll see the impulse response of LTI system. Now LTI systems are characterized by their impulse response. Let us say I have a system, I have some system, some T is some transformation. Now if I give input as del of t, if it is continuous system del of t, if it is let us say discrete system del of n, then some output you will get. That output we say impulse response. Okay, some system we have, if input, if we are giving impulse, as a response it is giving something output, that is called impulse response. Okay, now this impulse response completely explain the behavior of any LTI system. Okay, so the impulse response completely characterize the explain the behavior of any LTI system. Okay, now any LTI system we will represent by its impulse response. Okay, any LTI system we will represent with its impulse response. Okay, if we know the impulse response, we can explain about the complete behavior of any LTI system. Now, let us say any arbitrary input if we give as input in LTI system. If we give input as impulse, the output is nothing but impulse response. Now, if we give x of t some Ramakrishna, can you mute your video? Yeah, thank you. Now let us say if we are LTI system, it is characterized by its impulse response h of t, and x of t we are giving as input. Then let us say y of t is the output. Okay, then the output is given by the convolution of input and the input and the impulse response. Okay, for any arbitrary input, let us say for an LTI system, if I am giving input as del of t impulse, then output is nothing but impulse response. So generally any LTI system we represent in terms of impulse response, which is sufficient to explain the behavior of the entire system. Suppose for an LTI system with impulse response h of t, we are giving some arbitrary input x of t, then y of t is let us output, then output is given by the convolution of input and impulse response. Now how to define this convolution operation? You know very well, minus infinity to infinity x of tau h of t minus tau d tau, or minus infinity to plus infinity x of t minus tau h of tau d tau. Okay, assume that you are very well know about convolution and how to do it. So this is how we will define the output for an LTI system, which is the convolution of input and the impulse response of the system. Similarly, for the discrete system, let us say its impulse response is h of n, and we are giving x of n as input, then y of n as output. It is nothing but again convolution of input and impulse response. So it is something like this: k equal to minus infinity to infinity x of k h of n minus k, or x of n minus k into h of k. Okay, this is the output of any LTI system. That is nothing but the convolution. Okay, that means what? If we know the impulse response, then we can completely tell about the what will be the output for a arbitrary input for an LTI system. If we know the impulse response, we can say what will be its complete output for any arbitrary input. We can say that. Okay, Now, convolution property of impulse response, I think earlier also sometime back in earlier classes we have defined. So that is x of t convolved with t minus t naught. This is x of t minus t naught. Later you can try this in the convolution definition. You substitute it, then use the integral property of impulse response, that is area under impulse is 1, then you will get this. Okay, in many places convolution of any signal with respect to impulse will get the same signal. Okay, we use this property. Later you can try this. This is convolution property of impulse response. uh, is this okay till now? Is this okay? Any doubts? Okay, thank you. Now we will see about properties of impulse response or LTI systems. Okay, think you will study in systems, like in signals and systems, in the maybe in the first chapter you'll study about like different properties of systems, like different kind of systems. It's a memoryless, or is it causal, is it stable, like that you might have studied, right? Now let us say for an LTI system, only you are given only the impulse response of LTI system is given, nothing else is given. Now how to know whether that system is stable, causal, or memoryless, or memory invertible or non-invertible? How to check those we will see now. Now let us say we have some fine, we have, let us say y of t. First we'll see about causality. If h of t is given, whether the system is causal or not, we'll check. Now what is y of t of an LTI system? Minus infinity to infinity t, x of t minus tau, h of tau, d tau, right? Y of t is nothing but for an LTI system, x of t convolved with h of t. So this is the convolution definition. Now for a causal system, what is the condition? Can somebody tell me? What is a causal system?
Sir, its output depends on the present and past input.
Yes, its output should depend on the present and past inputs. It should not depend on the future inputs, right? Now, in this x of t minus tau, okay, if tau less than 0, then it is nothing but the future inputs, right? Isn't it?
Yes, sir. Yes, sir.
If it is tau less than 0, that means tau equal to, let us say, minus 2. If I take x of t plus 2, that means it is the future input, right? So the system should be, to be causal, then tau should be greater than or equal to 0, then only the system is causal, right? I mean, sorry, I don't say that, but the system to be causal, it should depend on the present or past values of the inputs. That means when tau is greater than or equal to 0, then only the present or past values of input, right? Right? When tau is 0, x of t, when tau is some positive quantity, let us say 3, x of t minus 3, past values, right? Fine, right? That means what? In this, that should to be causal, then for tau less than 0, right, h of t should be become 0. See, in this integral, for tau less than 0, if h of t is 0, then what will happen? So this entire thing I am splitting something like this. Tau equal to minus infinity to 0, x of t minus tau into h of tau d tau plus 0 to infinity x of t minus tau h of tau d tau. Now in this case x of t depending on the future values, right? Future values. Now the y of t is, or y of t should not depend on future values. Now how to make this 0? If I take h of t 0, h of tau 0, then this entire term will become 0, right? That means if h of tau 0 for tau less than 0, then the dependency on the future values of x of t will become removed. This will become 0. Is that okay? Is that okay? See, in this one, for tau less than 0, input have future values. So that we want to eliminate the dependency on future values. So for tau less than 0, h of tau, if we make 0, then it will not depend on the future values, right? So from this we can say when it is causal, an LTI system is causal only when, that is when h of tau is 0 or h of t, that is h of t is 0 for tau less than 0, then it is called causal. Okay, so an LTI system is causal if its impulse response is 0 for t less than 0. Sorry, if it is impulse response is 0 for t less than 0, then it is causal. Or impulse response h of n is 0 for discrete case, for n less than 0, then it is causal. Okay. Similarly, in the interest of time, directly I'll just read out the properties. Memoryless. What is a memoryless system? If the system depends on only on the present values of the input, then only it is memoryless, right? The system depends on present values of input, and it should not depend on either past or future values of input, then it is memoryless system, we will say. Now for an LTI system to be memoryless, if h of t is 0 for t not equal to 0, then it is called memoryless system. That means, let us say t equal to, it should depend only on the present values of the input. It should not depend on the past values of input. When h of t is 0 for t not equal to 0, then it is called memoryless. That means the impulse response should be some function of impulse del of t. Okay, the impulse response should be some function of del of t, then only it is memoryless system. Because if it is a function of del of t, definitely it is non-zero for t equal to 0, and it is 0 for t not equal to 0, right? We know how an impulse response, impulse looks like. At only t equal to 0 it is non-zero, other values it is 0. That means if the, what to say, the impulse response is a function of del of t, then it is a memoryless system. Okay na? If h of t is 0 when t not equal to 0, then it is memoryless system. Or h of n is 0 for n not equal to 0, that is memoryless. And the next important property is stability. Now, can somebody tell me when a system is called stable?
So if bounded input produces bounded output, then it
Yeah.
is.
Yes, bounded input produces bounded output. So let us say we have some system we have. I'm giving bounded input. That means input is less than something, some constant. Bounded means it is not infinite. And let us say for that input I get some output. If the output also bounded less than infinity, okay, sorry, less than infinity, then we will say the system is stable. Bounded input, bounded output. So for an LTI system, the stability condition is if the area under impulse response h of tau d tau, integral h of tau d tau, if it is some constant, that is which is less than infinity, that means the area under impulse response is some finite quantity. If it is less than infinity, then we will say an LTI system is stable. Okay, how to derive this? We can take this one, the impulse, this property we can take convolution. Now we take the modulus. Okay, now what we are taking is input, some bounded input we are giving. So input some finite quantity we are giving, right? So this is less than or equal to infinity, some finite quantity. So the what will happen if input is finite quantity? Definitely this is less than or equal to, let us say input is some c, input some finite quantity I'm telling. So input I'll say less than or equal to some constant c. Then here in this integral, this is just a shifted version of input. Definitely it is less than constant. Now this we can write like uh, this we can write like less than or equal to, so this is less than or equal to c, so we can write like this. This is constant, so actually y of this mod y also should be finite quantity. Now for that to be finite quantity, this second term should be finite quantity. So that one only. Area under this should be less than infinity, the same condition. Okay, so here modulus will take, magnitude will take. The area under the impulse response is finite quantity, then we will say that LTI system is stable system. Okay, now we have seen what is causality, what is stability, and what is memoryless conditions. On this we will try to solve some problems, then we'll get some idea. Yeah. An LTI system with impulse response is given as h of t equal to e power minus 3t u of t plus 2. Now you tell me whether the system is stable or causal or not. An LTI system with impulse response is given. For an LTI system, impulse response is given h of t. Now tell me the system is stable or causal or memoryless or what? First we will check for causality. First let us draw the signal. Now we know e of minus 3t how it looks. E of minus 3t something like this, right? Exponentially decaying. Okay, from minus infinity to plus infinity it will be, but u it is multiplied by u of t plus 2. That means for u of t plus 2 means what? This one, right? This is u of t plus 2. Both we have to multiply. Then what we get h of t is something like this we'll get. This is h of t. Okay. Now you tell me whether it is stable or not. First we'll check for stability. For stability, the area under this should be a finite quantity. You can find out the area under this, definitely you'll get a finite quantity. Since it is C, starting from here, after at t equal to infinity, it will become 0. So area under this definitely will get a finite quantity. That means integral minus infinity to infinity h of tau d tau. What will get? Minus 2 to infinity e power, how much this one? E power minus 3 tau d tau. Integration you can do, you will get some finite quantity. So it is stable. What about causality? It's non-causal, right? It is non-causal because for causal,
Causal and not memoryless.
for causality, what we told, for t less than 0, impulse response should be 0. But for t less than 0, impulse response is there, right? Is existing, right? So it's non-causal. And what about memory? It's memory or memoryless. Memoryless means for t not equal to 0, it should be 0. That means it should be a function of del of t, but it is not a function of del of t. So it is memory, system with memory, non-memoryless system we can say. Is that okay? Fine. Another question will solve the range of A and B, the range of A comma B for an LTI system. Let us say an LTI system with impulse response is given A power n for n greater than or equal to 0 and B power n for n less than or equal to 0. An impulse response of an LTI system is given. The range of A and B for an LTI system to be stable. So the question impulse response is given. So it is asked to find the condition on that A and B for which the system becomes stable. It's like mod A less than 0, mod A greater than 0, or mod B less than 0, something like that. Fine. What is the condition for stability in discrete case? So for stability, some sigma k equal to minus infinity to plus infinity, h of k should be finite quantity, right? Area under impulse response. Now this I can write k equal to minus infinity to 0. So b power k plus k equal to 0 to infinity a power k. Now, so this is what b power 0, b power 1, sorry, b power minus 1, b power minus 2, so on up to b power minus infinity. So this entire thing should be finite quantity. When that will happen, or else uh, this is what the second term is, what a power 0 plus a power 1 plus so on plus a power k. Then suppose here if mod a less than 1, let us say mod a less than 1, then it is what, it is gp, right? If mod a less than 1, it is gp. Yeah, so it is gp. What will happen? It is 1 by 1 minus mod a, gp infinite times sum of infinite terms. Okay, this is finite quantity. Here if mod be less than 1, okay, since negative powers it's going, right? Sorry, if mod be greater than 1, negative powers it's going, right? If mod be greater than 1 means, so 1, b power 0 is 1, 2 power minus 1, 2 power minus 2, like this. It will become a finite quantity. If mod be less than 1, if I take, let us say 0.5, so 1 plus 0.5 power minus 1 plus 0.5 power minus 2, what will happen? It will go to up to infinity. Okay, so in this case, if mod a less than 1 and if mod b greater than 1, then this summation will get finite quantity, then the system is stable. Okay.
Sir, can you explain again?
Uh,
How mod A less than 1 and mod B greater than 1 produces finite?
yeah, you see here sigma k equal to 0 to infinity a power k, right? So this is what a power 0 plus a power 1 plus a square plus a cube plus so on. Suppose let us say if mod a greater than 1, let us say 2, if you take mod a equal to 2. That means a equal to, then what will happen? 1 plus 2 square is 4 plus this will what happen? Then 2 cube is 8 up to infinity. It is an infinite quantity. Suppose if I take mod a less than 1, then what will happen? We know it, sum of infinite terms in gp is what, if 1 a plus, sorry, 1 plus r square plus so on, then it is what, 1 by 1 minus r, right? If mod a less
Yes,
than,
sir.
mod a less than 1 means first term is 1, second term is, let us say mod a is 0.1 if I'm taking, or 0.5 I'm taking, second term is 0.5, next term is 0.25, next term is 0.0625, like that, right? It is a finite quantity, right?
Sir, understood.
Yeah, similarly the second case is what, k equal to minus infinity to 0, b power k. So b power minus term is coming, minus power, so b power 0, b power minus 1, like this. In this case, if mod be greater than 1, we will get a finite quantity. Later you can check. I'm just skipping it in the interest of time. Fine. Now let us say two LTI systems are cascaded. Two systems are there, LTI systems. H1 of t, H2 of t. Then what is the overall system response? It's convolution of them, right? H1 of t convolved with H2 of t. Already you might have studied this. Okay. When the two systems are cascaded, then the overall response is nothing but the, or overall impulse response is nothing but convolution. When they are in parallel, like two LTI systems are in parallel, H1 of t, H2 of t, then what is the overall impulse response? Overall impulse response is nothing but the sum of the individual. Yes, added. Okay, I'm just moving little faster. Now let us say we have two systems, LTI systems. One is causal, another one is non-causal. Can the overall system is causal or non-causal? One is causal, another system is non-causal. Then what about the overall system? It's causal or non-causal?
It's non-causal.
Okay. It's need not be non-causal. Okay. So let us say we have one LTI system with impulse response del of some n plus 2, and another thing is del of n plus 3. Now what is overall impulse response? Del of n plus 2 convoluted del of n plus 3. Okay, one example I'm telling. So this is what del of n plus 2 plus 3 del of n plus 5. This is non-causal, right? Definitely this is non-causal. Now another case I'm just taking, one case where let us say the impulse response of first system is del of some n minus 6. Second system is n plus 3. Now what we will get, del of n minus 6 is causal, right? Convolved with del of n plus 3. This is what del of n minus 6 plus 3. So del of n minus 3. This is causal, right? Isn't it? What is the condition for causality? Condition for causality is what? If h of n or h of t equal to 0 for n less than 0, then the condition is condition for causality. Now here del of n minus 6 is causal because del of n minus 6 is somewhere at 6, it is having impulse, and del of n plus 3 is non-causal at somewhere minus 3 at negative values of n. This is causal, this is non-causal. What about del of n minus 3 at plus 3, right? It is causal, right? Is that okay? So need not be always non-causal. So two systems are cascaded. One is causal, another one is non-causal. Then it need not be non-causal always. Sometimes it can be causal. One example is this one. Okay. Now think. Let me just read out few properties. I think we are running out of time. Maybe in the next
Yes,
class.
sir. We will have other session also, sir.
Fine, fine, fine. Then we will stop here, and maybe in the next class we may see some other properties of LTI system and some problems we'll see. Any questions?
Sir, in next, can you please explain about sampling theorem? Not now.
Sampling theorem. Okay. I think I explained this in the previous classes. Okay. Anyway, we'll see in the next class.
Oh, yes, sir. Thank you, sir.
Yeah, previous lecture recordings are there. Somebody is asking. So in YouTube, you can search with my name. This is my name. Search with it with this name, so you will get all the recordings of the previous sessions. With the date, you will get. Just search with my name in YouTube.
Sir, what is name? Can you, sir, so once again? Name?
I messaged in the chat box. Can you see?
Okay, sir. Okay, sir.
Yeah. Any doubts? If you have any doubts, you can stay back, or else you can join the next session. Okay, thank you.